Yes, hopefully this works. I'm not sure. I think also the latency is pretty high, right? Whatever. Let's see if I can find the live stream. Yeah, here it is. Right, the cell. Okay. The cell. Okay. Okay, so the latency is not too bad. Alright, hopefully this stream doesn't crash at all. So yeah, we're gonna start. By the way, I'm gonna stream for like 1 hour because I was super stuffed schedule today, and I also woke up very late. So I don't have a lot of time at the moment, and I'm kind of like woken. So that's my bad. My alarm didn't go off. But we're gonna continue where we left off, or actually we did left off around here, I think. So I'm a bit behind of documenting everything. But so I will start documenting everything. And I think I'm right here. And also it's super hot here, so I'm a bit sweaty at the moment. In practice, to compute gradient, triangular C, we need to compute the gradients of each individual vector direction separately for each training input x, and then average them. Okay. Yeah, that kind of makes sense because we use partial derivatives, so we can only like calculate for one variable at the time. So that kind of makes sense. I wonder if there is a more better way of doing this, since doing each of the variables separately is taking a lot of time and resources. Oops, I made a triangle, or delta. It's a triangle. Yeah, so when it's very large, this can take a lot of time. And I did it called stochastic gradient descent, can be used to split up learning. I did is to estimate gradient triangular C by computing triangular ZX for small samples of randomly chosen training inputs. Yep. That makes sense. I'm gonna write it down. I'm not gonna write this whole paragraph, but I'm gonna write like a small bit of it. Okay. Yep, that can make sense. By averaging over the small sample, it turns out that we can quickly get a good estimate of the true gradient, triangular C, and this helps us to speed up gradient descent, and thus learning. To make these ideas more precise, stochastic gradient descent works by randomly picking out a small number of m of randomly chosen training inputs. We will label those random inputs training inputs x1, x2 to xm and refer to them as a mini batch. Provided the sample size m is large enough, we expect the average value of the triangular cxj will roughly equal to average overall triangular cx. That is all right. So we take a small peek out a small small number of m, and I cannot write. M of randomly. I think randomly is very important here as well, so just write it down. Chosen training inputs, chosen training inputs, and then I can just write the mathematical formula, which kind of makes sense. So it's the sum of over all the objects or the training based upon j, which is an index, and then we just sum the triangular c xj and then divided by the number of inputs we have, which is m. So that is like a mean, and that is almost the same as doing the thing for all training inputs. Divided by n, then n should be here as well, and that is equal to the triangular c. So you can like estimate triangular c, which is the gradient, by just taking a small batch of the amount of inputs you have, and then you have like a similar gradient. Very interesting. Where the second sum is over the entire set of the training data, swapping sides do we get this, which kind of makes sense. But I'm not gonna write it down because this thing here is equivalent to this. Confirming that we can estimate our gradient by computing gradients just for the randomly chosen mini batch. So we chose like a small batch of inputs, and then we just calculate the average or the mean of the inputs, and then we can actually say that they are equal to the gradient descent, right? To connect this explicitly to learning in neural networks, suppose WK and BL denote the weights and biases in our network. Then stochastic gradient descent works by picking out random chosen mini batch of training inputs and training with those. So you basically just do the delta movement for each individual parameter, which is the weight and biases. So I'll write this down as well, but it's kind of self-explanatory, I think, if you have read like the rest of the document. Otherwise, this is basically rubbish for someone who doesn't know the rest of the information. which makes sense because it's not it's difficult to understand a mathematical formula without the context behind it. But this is basically the partial derivative of the weights in the vector cxj, and it's also dependent on the index, and then we divide by the total of inputs, so we get a mean, and then we have a mean multiplied with a learning rate, which is negative, and then we have the initial weight, right? So we have a delta value here, or delta change, or a change in a function, you can say. I also dislike that they write L like this. Or maybe it's an I don't know, which this is not my intention. But either way, I'm gonna write it as an L. So if you want to like do your own machine learning library, you can basically do that with all of these basic functionalities in mathematics. You just have to program in everything in a like a module type infrastructure, and then you're good to go. Where the sums are over all the training examples xj in the current mini batch. When we pick out another randomly chosen mini batch, the training with those, and so on, until we exhausted the training inputs, which is said to complete an epoch of training at the point we start over with new training epoch. I think that is like a good notation to write down. It's not super important, but it gives you like a fundamentally what an epoch actually does. So I think that is a good way to understand how this works out. Let me pick out another randomly chosen image. Random. But yeah, I'm just gonna like stream for 1 hour, okay, and then I will probably stream for another hour someday later, because I'm stupid and oversleep. I kind of needed that though, because I like studied a ton of Japanese yesterday, so I was quite tired. And what I'm probably gonna do like today is after this going to the gym and train legs, and then I'm gonna go home to write like a super important email. And then I'm probably gonna go home and like study Japanese for at least 4 hours, and probably stay up to like 1 or 2 o'clock in the morning. That's the plan. And hopefully be able to be with my family a little bit, because I have to focus on that as well, since I will be going abroad for like 1 year. So I want to see them in 1 year basically. I also have to read through like some academic material for my academic advisor, because I'm gonna have like a meeting with him. So I have to know a little bit what he's been doing. And he's been doing a lot, so I probably want to read through everything, but I will read through a decent amount, I think. Right. Incidentally, it's worth noting that the conventions vary about scaling of the cost function and mini-batch updates to the weights and biases. In equation 6, we scaled overall cost function by a factor of 1 divided by n. People sometimes omit the 1 divided by n, summing over the costs of the individual training examples instead of averaging. This is particularly useful when the total number of training examples isn't known in advance. This can kind of occur if more training data is being generated in real time. For instance, in a similar way, the mini-batch update rules 2021 and sometimes omit the 1 divided by m term out the front of the songs. Conceptually, this makes a little difference, since it's equivalent to rescaling the learning rate, but when doing detailed comparisons of different work, it's worth watching out for. So basically what they're saying is that if you have a retrained neural network and you don't know the total amount of inputs you have, you can essentially like skip dividing by the number of inputs and do that afterwards. But if you're gonna like compare different neural networks with each other, you have to take in consideration that you haven't calculated the mean. We can think of a stochastic gradient descent as being like political pooling. It's much easier to sample a small mini-batch than it is to apply gradient descent to a full batch. Just carrying out a pool is easier than running out a full election. For example, if we have a training set of size n, which is equal to 60,000, as in the MNIST, and choose a mini-batch size of, say, m equal to 10, this means we will get a factor of 6,000. Speed up in estimating the gradient. Of course, the estimate won't be perfect. There will be a stochastical fluctuations, but it doesn't need to be perfect. All we really care about is moving in a general direction that will help decrease C, and that means we don't need an exact computation of the gradient. And in practice, stochastic gradient descent is commonly used and powerful technique for learning in neural networks. And it's the basis for the most of the learning techniques we will develop in this book. And we will jump over the exercise. Let's conclude this section by discussing a point that sometimes bugs people: new gradient descent. In general, in neural networks, the cost of C is of course a function of many variables, all the weights and biases, and so in some sense defines a surface in a very high dimensional space. Some people get hung up and thinking, hey, I have to be able to visualize all these extra dimensions, and then may start to worry. I can't think of in 4 dimensions, let alone 5 or 5 million. Is there some special ability they are missing? Some ability that real super mathematicians have? Of course, the answer is no. Even most professional mathematicians don't visualize 4 dimensions especially well, if at all. The trick they use instead is to develop other ways of representing what's going on. That's exactly what we did. Above. We used an algebraic rather than visual representation of delta C to figure out how to move so as the decrease of C. People who are good at thinking in high dimensions have a mental library containing many different techniques along these lines. Our algebraic trick is just one example. Those techniques may not have the simplicity we are accustomed to when visualizing 3 dimensions. But once you build up a library of such techniques, you can pretty good at thinking in high dimensions. It won't go into more detail here, but if you're interested, then you may enjoy reading the discussion of some of the techniques professional mathematicians use to think in high dimensions. While some of the techniques discussed are quite complex, much of the best content is intuitive and accessible, and could be mastered by anyone. Okay. I think they start doing the code here now, yeah. So implementing our network to classify digits, right? So they're gonna write like a Python program, which is not ideal for neural networks. It's actually, I think, the most ideal language to use C++ or C. But C++ has more support for neural networks and graphical calculations, which is matrix multiplications. All right, so let's write a program that learns how to recognize handwritten digits using stochastic gradient descent and then MNIST training data. We will do this, but with a short Python 2.7 program, just 74 lines of code. The first thing we need is to get the MNIST data. If you are a Git user, then you can obtain the data by cloning the code repository for this book, which is this link here. Wonder if this actually kind of works. Let's see. I didn't copy it. Okay, you cannot copy it. Either way, if you don't use Git, then you can download the data here. And this PDF is not hyperlinked. Oh, okay. Incidentally, when I described the MNIST data earlier, I said it was split into 60,000 training images and 10,000 test images. That's the official MNIST description. Actually, we're going to split the data a little differently. We will leave the test images as is, but split the 60,000 image MNIST training set into two parts of a set of 50,000 images, which we will use to train our neural network, and separate 10,000 images validation set. Yeah, so they use a 90 to 10% rule here. And we won't use the validation data in this chapter, but later in the book we will find it useful in figuring out how to set certain hyperparameters of the neural network. Things like the learning rate and so on, which aren't directly selected by our learning algorithm, although the validation data isn't part of the original MNIST specification. Many people use MNIST in this fashion, and the use of validation data is common in neural networks. When I refer to the MNIST training data from now on, I will be referring to the 50,000 image dataset, not the original 60,000 image dataset. Apart from the MNIST data, we also need a Python library called NumPy for doing fast linear algebra. And NumPy is programmed in C++ and C, by the way, so it's super fast. So they use like C and C++ wrappers in Python. If you don't already have NumPy installed, you can get it here, whatever. We are not gonna code a lot. I'm actually gonna code on paper. So if you guys don't know, I have like a paper here. So I'm gonna write the code on this paper, which I find is very intuitive if you like want to have like a good understanding of how code actually works. So let me explain the core features of neural networks code before giving a full listing below. The centerpiece is a network class, which we use to represent a neural network. Here's the code we use to initialize a network object. So they basically just create a class which is called network, and this network have a number of layers, which is based upon the given size. And then we have size, biases, and this is just a random, okay, so this just initialize the biases with random numbers. And then we do the same for the weights. So we just have random weights and numbers, which is, you know, the standard thing to have. But I'm gonna write this class down, you know? You can also do this with pseudocode, but I'm not gonna go into that. And remember, this type of function here basically sets values to initialize the variables that the class have. So when you instantiate the class, you will basically set these values. And by the way, by just writing code on a piece of paper kind of remind me of doing exams. It's kind of funny. Okay. And then we set the weights in the same way, but it's different, I think. Yeah, because the weights can be a matrix, but the biases has to be a vector, right? Okay, so they basically do. Okay, that kind of makes sense. This is gonna be quite long of code base. I think I'm gonna actually do what they're doing in the code and, you know, just break the line. So I'm gonna rewrite some stuff here, but that's fine. But what zip is basically doing is just taking data structure which contains of multiple arrays, nested arrays, and then just compress it to one array. Is it -1? It's -1. Okay, interesting. So -1 is actually the last. I think in this case the last of row, I think, and then we have the first row. So we zip the last and the first row. Now, in this code, the list size contains the number of neurons in the respective layers. So, for example, if we want to create a network object with 2 neurons in the first layer, 3 neurons in the second layer, and 1 neuron in the final layer, we do this code with the code. Okay. So net is equal to network 1, 2, 2, 3, and 1, which basically says the input layer is based upon 2 neurons, the hidden layer is based upon 3 neurons, and the output layer is based upon 1 layer. That is good to note. So I'm gonna like create a comment here in Python. Okay. The biases and weights in the network object are initialized randomly using NumPy randomized function to generate Gaussian distributions with mean 0 and standard deviation is 1. This random gives our stochastic gradient descent algorithm a place to start from. In the later chapters, we will find a better ways to initializing the weights and biases, but this will do for now. Note that the network initialization code assumes that the first layer of neurons is an input layer, and omits to set any biases for those neurons, since biases are only ever used in computing the outputs from the later layers. Note also that the biases and weights are stored as lists NumPy matrices. So for example, net.weights1 is a NumPy matrix storing the weights connection to second and third layers of neurons. It's not the first and second layer since Python list indexing starts at 0. This is just basic programming. But what they're basically saying that since weights are matrices, this is when you type in the number 1 here, it's basically the second row in the matrix. Right? Since net.weights is rather verbose, let's just denote that matrix W. It's a matrix such that WJK, where J is probably the rows and K is the columns. It's the weight for the connection between the kth neuron in the second layer and the jth neuron in the third layer. This ordering of the J and K indices may seem strange. Surely it would make more sense to swap J and K indices around. The big advantage of using this ordering is it means that the vector of activations of the third layer is this, which is a sigmoid function. Right? So the A prime is basically a sigmoid function. Right? This is quite a bit going on in this equation, so let's unpack it piece by piece. A is the vector of activations of the second layer of neurons. To the obtained A prime, we multiply A by the weight of matrices, and when they say multiply, they mean matrix multiplication. And then add the vector B of bias, which is this one here, and remember this here is probably negative. We then apply the function sigmoid function element-wise to every entry in the vector, right? This is called vectorization, the function sigmoid. It's easy to verify that the equation of 22 gives the same result as our earlier rule, equation 4, for computing the output of a sigmoid neuron, which is basically equation 22 is up somewhere here. No? It's, did I go? It's here, yeah. And then, so this equals to equation 4, and equation 4 is like all the way up here. Maybe I did go up a little bit too much. That's 1, 2, 3, 4. So this is the same as the vectorization that we did see in equation 22, right? I'm just gonna go scroll down to everything else that we did go through. We've actually been doing a lot good this time. We have gone through like 30 amount of pages, a lot of different pages. Yeah. Okay. So we said that basically. So write an equation of 22 in component form and verify that it gives the same result as the rule 4 for computing the output of a sigma neuron. We're not gonna do this because that means that I have to code. I'm not gonna code at the moment. Yeah, with all this in mind, it's easy to write code computing the output from a network instance. We begin by defining the sigmoid function. So this is the sigmoid function. But I wonder here now, since we have like a division, is it possible to get divided by 0? No, it's not, because this is this can be 0, but this cannot be 0. So never mind. You know, it actually cannot be 0 when I think about it. Nothing of this can be 0. The answer or like the value of the output can be 0, but we can never divide by 0. So that's a good thing. It's defined on the 0 interval. Note that when the output z is a vector of numpy array, numpy automatically applies the function sigmoid elementwise, that is in the vectorized form. Then add a feed forward method to the network class, which give an input A for the network returns the corresponding output of everything. All the method thus applies equation 22 for each layer. Right, so for each or for each bias and weight, B and W, right? Bias and weight. In the compressed array, that's why we use a zip function, because we have nested arrays, right? Self, which is defined by the way. Self.biases. Self.weights. Right? And then we apply the sigmoid function on A. Okay. You know, just to clarify, this sigma function has to be in the same class here. So this function here is in the class, and this as well. And np.dot stands for the matrix multiplication between the weights and the inputs. Just do it. Which is the biases, right? Of course, the main thing we want our network objects to do is to learn. To do that, to that end, we will give them a styd method which implements stochastic gradient descent. So this basically says stochastic gradient descent. Here's the code. It's a little bit mysterious in a few places, but it will break down. I will break it down below and the listing. Okay, so holy shit, there is a lot of like this explanation of this. Do I want to type that all out? Probably not here. No, I'm gonna turn pages here. Send. This is probably gonna take some time to write down. You know what? We could actually go through the function before we start writing it down. Okay, so if we have test data, then we set the number of tests equal to the length of the test data, right? And then the n is the length of the training data. Okay.